Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to be going over the Unit 3, Circular Motion Gravitation. First question review from this unit. Let's go and take a look. Okay, so we have this merry-go-round, this kind of wheel, and it's spinning this way. It's got a radius r. Radius of r, and it's got these compartments inside, and inside these compartments there is a table and there's a book on the table in each of these compartments while this thing is spinning. Let's take a look. So, passenger compartment in a rotating amusement park contains a bench on which a book of mass MB, massive book, is placed, as indicated by the dot in the left of the figure. The compartment moves with a constant angular speed. Okay, so constant angular speed about the center of the ride along a circular path of radius r. The bench remains horizontal throughout the compartment's motion. The right figure above shows a magnified view of the compartment. Okay, so these never go on an incline, so you never have to worry about an angle because they're always horizontal, the bench. Okay, boom. The graph below shows the horizontal component of the book's position as a function of time, where positive x direction is to the right. Determine the period of revolution of the book. Okay. So pretty much starts at 0. So this book starts at 0. Here's x equals 0. I'm going to cut off right there. Here's x equals 0. Over here is negative, and over here is positive. So it'll start going negative, and then it'll go back to 0. And it'll become positive, go back to 0. That's what we see here. Go negative, come back to 0. Go positive, come back to 0. So once you determine the period of revolution of the book, or how long does it take to get back to the same spot, complete one revolution. So from here to here, that is one revolution. And it looks like this is 100 seconds right here. So this should be, well, there's 1, 2, 3, 4, 5 equally spaced lines here, so this must be 120. Okay, so the period, t, is 120 seconds. Calculate the tangential speed of the book, VB, not the angular speed of the book. Okay, so what's the difference? Tangential speed is how fast this fly is moving, and it's represented by this vector arrow v here. Okay, so how fast that fly is moving. Notice that if a fly were here, this fly would be moving faster than this fly. Okay, however, they would both have the same angular speed or angular velocity. Okay, because they would both complete a rotation at the same time. However, the one further out would be moving faster than this one. This one's tangential velocity vector would look like that. Okay, so how would we find that? Okay, well, if you look at your equation sheet, you'll find an equation that looks like this. It's t equals 2 pi over omega. Okay? It looks like this. The period equals 2 pi divided by the angular speed. Okay? If this is not on your equation sheet, however, since the exam this year is open book, I would write these down. Okay? So we have linear quantities moving in a line, and we have rotational quantities moving rotationally. Okay? We have, for linear, we have displacement, but for rotational, we have angular displacement. And the way you can get between one and the other, let's see, I'll put it right here, equation. This is x equals the radius times the angular displacement. Okay. What if I were talking about tangential velocity? Well, it's angular velocity, right? And so this is just our, like that. Good. And we have tangential acceleration, and we have rotational acceleration. And to get between those, it's a equals just the radius times that one. Alright. So these are not on the equation sheet. So I would have them written down somewhere so you have those, because the test this here is open book. Okay. Perfect. Okay, so we know the period is 2 pi over omega. This is on your equation sheet. We said that the period was, so let's rearrange this. So that means this equals 2 pi over t. That means the angular speed is 2 pi. We already said the period was 120. Okay. Now we found the angular speed. Let's find the tangential speed. Okay. Using this equation right here, we know that v equals r times omega. So that means the radius was radius r. Okay, we get the radius from this graph here. Okay, it says it's the horizontal component of the book. Okay, we can see that the maximum distance away the book gets is 30 meters. So that must be the radius. That's where we find the radius. So that means 30 times omega is the velocity. So that means v equals 30 times 2 pi over 120. And eventually that came out to 1.6 meters per second. Okay. On the dot below, it says draw free body diagram. Each force must be represented by a distinct arrow starting on, pointing away from the dot. Okay. This was worth 3 points out of a 12 point. So again, 1/4 just comes from free body diagram. I'm going to draw the free body diagram over here. Okay. Now, this book is undergoing circular motion. Okay. What do we, for an object to undergo circular motion, there has to be a centripetal force, right? What does centripetal force mean? It means it's a force pointing towards the center. So for all of these to go in a circle, it has to have a centripetal force. That means the net force on all of these points to the center. And this is true for a planet orbiting a sun. This is true for a ball tied on a string being swung around. Okay, this is true of a car going over a hill or into a dip. Okay, these are all examples of circular motion, and they all have forces pointing towards the center, the net force. Okay, so we know that this book has a force of gravity like this, because it has mass. What is the force that is causing the centripetal force which causes circular motion? In this case, it's the normal force caused by the surface of the table. And we know since the net force has to point towards the middle, the normal force has to be greater than the force of gravity, because there needs to be a net force pointing towards the middle. Remember, we're looking at the book at the lowest point. So we're looking at the book at this point right here. So we know that the net force here has to be pointing towards the center of the circle, which means the normal force has to be greater than the force of gravity for the net force to point towards the middle of the circle. At the lowest point in the circular path, the book is only moving in the horizontal direction. In what direction is the net vertical force? Well, we already drew this. In the previous one, we said that here the only forces acting on the book, the normal force and the force of gravity. Okay? So the book is accelerating this way, the velocity is moving this way. Right? Remember we said if we cut the string, we were like, we had this ball on the string that we were swinging around in a circle, and if we cut the string, which way would the ball go? If we cut the string here, the ball would move tangentially to the circle. Okay, so even though the ball is moving this way to the right, the acceleration or the force points inward, okay, which is the up direction. Well, deriving any equations, briefly explain your reasoning in terms of the book of motion. You can say the book is undergoing circular motion, and a centripetal force, causes circular motion. And centripetal force, remember, this means center seeking. So therefore it has a net force pointing towards the center, which in this scenario would be upward. Center seeking. Good. Derive an equation for the vertical force that the bench exerts, okay? So let's go to our trusty little equation here. Sum of the forces is equals ma, okay? A couple of things. These are centripetal forces, right? And this is centripetal acceleration. Okay? Remember, centripetal forces only point upward or towards the center of the circle and away from the center of the circle. And remember, forces that point towards the center of the circle we define as positive. Forces that point away from the center of the circle we define as negative. Okay? So, force normal is a force that points towards the center of the circle, so it's positive, while force of gravity points away from the center of the circle, so we're going to define that as negative. Okay? That equals to m. Remember, the centripetal acceleration, this is on your equation sheet, we can replace it with v squared over r. So this is actually v squared over r, and this is the mass of the book, right? Perfect. So now we just have to rearrange for force normal. That means force normal equals this mvb squared over r plus, plus, that's right, because we'll move the force of gravity to this side, plus mg. Okay? And there you go, that's your answer. If you'd like, you can rewrite this, but you don't have to. This is force normal equals, we can factor out the mb, and you don't have to do the step, and that'll be v squared over r plus g equals force normal. Part D. At the lowest point, is the force that the bench exerts on the book greater than, less than, or equal to the weight of the book? We already said it was greater than, right? We said that the force normal had to be greater than the force of gravity. This is because we needed a net force pointing towards the center, which is called the centripetal force. Okay? And that's how this book is able to stay in circular motion.